Okay, we're going to continue on here, chapter 2. Hopefully your first day of lab went okay. Yeah, hopefully. Yeah. All right. So in chapter 2, we were talking about measurements. Remember, as we talked about and as you did today, whenever you take a measurement, again, there is some degree of uncertainty within that measurement. There's some degree of estimation that you need to make. And remember that whenever you take any type of measurement, when you look at the piece of equipment, you really want to sort of identify really two markings will help you out. There's sort of large markings and there's kind of small markings. And again, what you're looking for is how many of each you sort of have. So when we look at the large markings, remember that these usually will have some type of number associated with them. So again, in this case, our large marking, we have a 1 and we have a 2. And simply all you have to do, right, is subtract those two, and it'll tell you basically what it represents. So our large markings here represent 1 centimeter as we do so. Now, the other important markings on the scale are what are small markings. And these are usually the markings that are between these two large markings. And you want to count again how many of those you have. And as we talked about last time, it's important to start counting after the last large marking and continue sort of counting until you hit the next large marking. So in this case, we would go here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we do have 10 markings that's between our large markings. So if we just simply divide our large markings by 10, which is how many we have of the smaller markings, that will tell us that each of these smaller markings is 0.1 centimeter. And again, that would be something like 1.1, 1.2, 1.3, and so forth as you go through there, all the way up to 2. So, if we did have something in this area here, we want to make sure that we do take the proper reading. Now, how far can we take the proper reading? We also talked about this last time, that typically speaking, you could go one more place to the right of the smallest marking. Or if you want to know for sure, all you have to do is take the smallest marking basically and divide it by 2. And that will give you your kind of plus and minuses, tolerance or precision or uncertainty that we talked about. And in this case, that would give us 0.05 centimeters. That means that when we look at this, there should be, as we talked about last time, some numbers that everybody agrees upon that the measurement is at least that much. And in this case, it would be like 1.3. These are what are again referred to in a lot of cases as the certain numbers. And when you take a measurement, you should always record the certain numbers. But the next part of it is really where the uncertainty or estimation comes into play. So what you want to kind of think about is, about where that is at. You may think, well, in this case, maybe it's a little bit more than halfway, but it's not quite obviously to the 1.4. So maybe we record something like 1.38 centimeters, always including the units as we talked about. And that's our first uncertain number when we take this measurement. Now, when we do that, that is basically what significant figures are. And in this particular case, this measurement here would have 3 significant figures, where the uncertainty or estimation is in that last significant figure, in this case, an 8. We can incorporate this into our measurements, which they really like you to do in this school when you're in lab and so forth. And probably the proper way to record this would be 1.38 centimeters plus or minus 0.05 centimeters. Now, what the plus or minus really tells you, in addition to sort of the uncertainty there in the measurement, is you can really use it to be for sure how far you should take the reading to. So when we look at this plus or minus, that is 2 decimal places, and that's exactly where we took our proper measurement to. So again, if for sure when you look at the scale, you know what the smallest markings represent, then you could simply just divide it by 2, and then you'll know pretty much how far you should take the reading to. Again, that's also how you get the plus or minus in terms of your measurement, which is really sort of the uncertainty in that last digit. Most people do sort of consider the last digit plus or minus 1, but technically it could have that much sort of leeway in it. This also works for something like we saw last time, where maybe I think we had a scaling of something like this. It was like 20. Let's call this like milliliters here. And in this case, the difference between our large marking is 10 milliliters. Here we have 1, 2, 3, 4, and 5 markings only between the large markings. Again, if we divide that by 5, that gives you your small markings represent 2 milliliters in this case. That means that if we divide our smallest marking by 2, it is going to be plus or minus 1 milliliter. That means if you have a scale again like this, and you find yourself sort of here in the middle, we'll call it, that's basically 22, that's 24. As we talked about last time, in the middle, 23, 2 and 24, the best you could do is something like 23 milliliters, where this would have two significant figures, where the 3 is the uncertain number, our estimated number in this particular case. Again, the reason why we really can't go any further than that, as we talked about last time, you really don't know, for example, here where 22 stops and 23 starts, right? There's not enough sort of space between those two markings to sort of figure out where, one begins and one ends. So if things do change depending on the scale that you use, you want to always look at those. You want to always take the reading to the proper number of significant figures. And again, here at this school, they do usually want you to include the plus or minus when you're in lab and stuff like that, taking measurements. So when you do these things, you always want to take it to the proper number of significant figures. Remember that you also end up exactly on a marking, dead on an actual number. You basically need to include a proper number of zeros to keep the number of significant figures correct. Now, it's important not to add too many, right? Because if you add too many significant figures, you're now making your measurement much better than it should be. And if you are taking away significant figures, then you're making your measurement a lot worse than it should be. So you got to always try to get it to the right number. Any questions on that stuff we talked about last time there? All right, so let's take a look at some more examples of this. As we mentioned before, when we take any type of measurement, that is really where significant figures come from. And you want to record all the certain numbers plus the first uncertain number. And again, those are significant figures. That also brings us to an idea of a couple important differences between two words that are sometimes interchangeable or used interchangeable, even though they really shouldn't be. And that is accuracy and precision. So there is a difference between accuracy and precision. When we talk about accuracy or being accurate, what that really means is how close you are to the true value. So if there is a true value, a correct value, and you're very accurate, that means that your number is very close to what the actual number should be. Precision, on the other hand, is how close a set of numbers are to themselves. Now, you can be very precise, but not very accurate. And what I mean by that is you could do an experiment 3, 4 times, and you could do it wrong the same way 3 or 4 times and follow the same wrong procedure and get the same answer. Although that answer you get is precise because you redid it 4 times wrong, it is not necessarily accurate because it's nowhere near the right answer because you did something wrong in the process. So ideally, when we're doing chemistry or any science, we want to be both accurate and precise. And a lot of times we look at, for example, if we threw darts at a bullseye, the goal here is to hit the dead center there. So if I throw some darts and I hit here, I hit off the board, and maybe hit over here, am I very precise? Not really. Those guys are all over the place, including missing the board completely, right? Am I accurate? Not really either, because the goal here is to get the bullseye in the center, right? So I did not get that. So in this case, I'm not accurate. I'm not precise. So, I pick up my darts and go double or nothing. We'll give it a go and see what happens. That. And I take my darts and I throw them and I go boom, boom, boom. Am I precise? I am precise. They all hit pretty much the same spot, right? Am I accurate? I'm not. I'm precisely not accurate, right? Which means you could definitely be pretty precise and do something, like I said before, over and over the exact same way. You'll get the same result. That old saying, right? If you do something the same time over and over again, you're going to get the same results, right? So you can definitely be precise, but not very accurate. I go triple or nothing here in this case, and I pick up my darts. We don't read the board. There we go. And I throw my darts at this case here, and I go boom, boom, boom. Am I precise? Am I accurate? I'm both, right? And again, that is the goal when you're doing science or experiments. You want to be accurate. You also want to be precise. We look at precision a lot of times when we do experiments by doing multiple trials. So when you do an experiment, maybe you do the same experiment multiple times. The idea of that is when we look at precision to see if something is reproducible, right? So if you keep getting kind of the same answer through this procedure, is a reproducible type of procedure. Accuracy, again, tells us how close we are to the right number. So sometimes when we look at accuracy, percent error is something that we calculate to look at accuracy. And that is a measure of how close your number was really to the true number. We usually want a really small percent error. Really large percent error usually means you did something not so great. You kind of screwed up somewhere along the way. When we talk about precision, a lot of times we look at standard deviation, maybe percent standard deviation. And deviation or percent standard deviation, they're basically calculated based off of the average values that you get. So that kind of puts all the numbers that you got kind of comparative to themselves, and you come up with sort of a deviation. Also, usually we want a relatively small deviation when we're talking about precision. Question. So again, here's our example. On the guy on the left there, we're all over the place, so we're not accurate or precise. Guy in the middle, we did sort of hit all those guys in the same area. So we are going to be precise, but not very accurate. And in the last one there, we got the middle, like my example there, and we hit everything all near each other, so we're accurate and precise. So again, in measurements, we're looking to basically do both things, be accurate and precise when we take our measurements. All right, so let's take a look at some more examples here. So what should be the proper reading of this line here? The numbers go with the bigger lines. They're kind of off-center there, but they kind of go with those lines. All right, so take a moment, figure out what the proper reading is to the proper plus or minus there, or uncertainty here. It should be based on this scale. Okay, so let's take a look. So once again, when we look at this, we want to look at the scaling. So our large ones are the ones with numbers. So we have a 2 and we have a 3. So if you subtract that difference here, 1 centimeter is going to be our difference. We look at our smaller markings. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 smaller markings, so we just divide that by 10. That tells us each of the smallest markings is 0.1 centimeters. That means right around here is 2.5. This guy would be 2.6. Right there would be 2.7 in this case. We could clearly see, as we talked about, we want to record the certain numbers, so 2.6 definitely should be certain here. It is not exactly 2.7 in this case, and it's definitely past 2.6. We once again could take our smallest markings, divide it by 2, and that's going to tell us we should really take this reading to plus or minus 0.05 centimeters. For all intents and purposes, that is 2 decimal places. So we do need to add one more, which is our estimated digit in this case. And in this case, it looks like it's fairly close to the 2.7. So it looks like they went with a 9, which would be our first uncertain number. And obviously our units as well. Putting all that together, 2.69 centimeters plus or minus 0.05 centimeters. That looks like that guy right there. That would have how many significant figures? How many significant figures? It would have 3 significant figures, right? The uncertain digit here being our 9 in this particular case. This is why this is not good. That would have only 2 significant figures, right? The 2.6. This guy would have 3 significant figures, but definitely is more than 2.5, so that is no good. That is 2.67, which is an okay measurement, except they actually threw an extra 0 in there, which means it now has 4 significant figures, which, much like going with less numbers of significant figures, going with more significant figures is not good either, because you do not have the ability on this scale to go that far in terms of your measurement. This is the right one, and obviously the plus or minus is incorrect on this particular one here. Yeah. Questions on that one there? All right, so do the red line here, same deal, big numbers go with bigger lines there. All right, so looking at this one, same deal. We got kind of the same scale going on there. That's an 8, that's a 9. So our large marking is going to be 1 centimeter. If we count up our little kind of smaller markings, we do have 10 of them as we go all the way across. So that's going to give us a small marking of 0.1 centimeters in this particular case. Here again, if we divide our smallest marking by 2, I know I really should be doing a plus or minus 0.05 centimeters. So since it's multiple choice, that clearly gets rid of those 2 for sure, right? So in this case, when we look at this 9 is really 9.0. That is 9.1. So we're somewhere between 9.0 and 9.1 in this case. So certainly we are 9.0, which is our certain numbers. In this case, it looks like it's just past the 9 line there. So 9.02 is the one we will go with, plus or minus 0.05. Again, this has too many significant figures based on how far you should take the reading, right? So this is correct, actually, in this case. This would be an incorrect reading in this case, as it goes too many digits, because that would have 4 significant figures. This guy would have 3 significant figures in this case, with the uncertain number being the 2 in this particular case. Questions on that one there? All right. So when we look at volume in something like a graduated cylinder, for example, we do look at the meniscus, as we talked about last time. That is the curvature of the liquid. We typically will see a meniscus that is this kind of U-shaped meniscus, and we always read from the bottom of the meniscus. Again, that's because on the sides, because of the interaction with the glass, the liquid is coming up, and that's not really the volume, it's just a result of that capillary action. So without that, in the center, which is kind of the middle or the bottom of this meniscus, we will actually see what the true volume actually is. Sometimes much easier to see in something like a graduated cylinder, for example, than something like a beaker. A beaker is a crappy piece of equipment, for example, to use to take any type of volume measurements and stuff like that. You would be very surprised, and you might do this throughout the course of your lab or whatever it may be. You might fill up a beaker to the 50 mil mark and like pour it over into graduated cylinder, and see you're like nowhere near 50 mils, even though it's at the 50 mil mark. That's because a beaker typically has a very big opening, which spreads out the meniscus, makes it very hard to read exactly where it is, as opposed to something like a graduated cylinder, smaller opening, more defined meniscus, a little bit better way of reading it. So in something like a graduated cylinder, we fill from the top, we pour out the top, so the volume increases from the bottom of the graduated cylinder readings to the top. So if we look at something like this here, we have a 30 and a 40. Difference here in terms of our large markings is 10 milliliters. If we mark it up here, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. Between them gives us some small markings of 1 milliliter in this case. And because of that, we can divide that by 2, and we know really in this case, we should take our readings to 0.1 milliliters if we, I'm sorry, 0.05. There you go. There. 0.5. I divide that by 2. There you go. So if we do that, that'll tell us basically how far we should take the reading to. And in that case, why don't you take a moment and see what reading you would give on this particular one here. So if we look at this again, each of these are 1, so 31, 32. The big line here is 35. Next line is 36. And the next line is 37. So our meniscus is between basically the 36 and 37 spot. So we definitely going to write 36, which would be our certain numbers. Now that uncertain number tells us, right, we should take it to 1 decimal place here. And again, this is where the estimation comes into play. And I think maybe they went with 8, as they felt it was closer perhaps to the 37 and milliliters. Again, including the plus or minus here, 0.5 milliliters. Again, telling us we should go to 1 decimal place, which is what we did. This would have 3 significant figures, with the 8 in this case being the estimated digit or uncertain digit. Now, the estimated digit or uncertain digit is not always, just so you know, not always the last digit that is written, but it should be the last significant figure that is present. So a lot of times it is the last digit that's written, but not 100% of the time, like 99% of the time. But there are some times when it is not the last digit that's actually written in the measurement, but it should always be the last significant figure. So you want to keep that in mind. Question. Now, another very common piece of equipment that we use is a burette, and a burette actually has what's referred to as a stopcock on the bottom there. That's kind of what opens it and shuts it. You fill it from the top, fill the liquid from the top, and you dispense it basically from the bottom. Now, when we look at a burette, it is a different scaling, and that's why you always want to look at the piece of equipment that you're using to understand how the scale sort of works. So, for example, if you go to the very top here and you fill it up, that is basically 0 milliliters. Then it goes 1, it goes 2, it goes 3, and so forth. It actually increases as you go down on the scale in this case. And that oftentimes will lead to people making incorrect measurements. So, for example, if your meniscus was between the 1 and the 2 mark and you're using a burette, the volume is actually 1 point something here, not 2 point something. So again, it increases as you go down because you're emptying out the bottom in this case. So the volume actually does increase as you go down. You still want to kind of do the same thing, see how far you can take the reading to. So why don't you give it a go here and see what you would come up for this guy here. Let's see what you would get. Okay, so once again, we want to look at the scaling. So we're going to go with our large marking. So that's a 29 and a 28. Difference between that is 1 milliliter. Here, if we count up our markings between them, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, if we divide that by 10, that is going to give us 0.1 milliliters as our smaller markings. And once again, we could get our uncertainty here by dividing by 2. Try not to screw it up this time. There you go, 0.05 plus or minus in terms of that. So again, that kind of dividing the smallest marking by 2 automatically tells you really how far you should take a proper reading. In this case, we should take it to 2 decimal places. Clearly, that is 28.5 there. So that's 28.6, 28.7, 28.8, and then that is 29. So it's at least 28.8. That's going to be our certain numbers in this case, as you can see here, 28.8. And now our uncertain number, which in this case they feel it is about halfway between these 2 markings, the meniscus, and we will go with 5. That gives us here 4 significant figures with our uncertainty again to that second decimal place. Questions on that? So it's really important when you use a burette, whenever you use a burette, that you don't screw up your experiment, that you actually take a reading of exactly what the number says. Very common what people will do is, for example, let's just say this was a 50 milliliter burette. And what they commonly will do, people, when they use this, is they'll fill it to the very top and go, cool, that's 50. And they will get really the wrong measurements for their experiment. So you should never do that. People do that all the time when they use this piece of equipment. Again, you fill it to the top, you read the exact number it's at, which in most cases should be 0.00 in most cases up there on top. And when you use whatever you use, you let it drain down, you take another reading. That's how you do this, by the way. You usually take 2 readings. You take an initial reading wherever you're starting. You drain down whatever you're using. You take a final reading, and then you can find the volume you use by taking the final minus the initial. So whenever you use a burette, like you'll do in a later experiment in the semester through titrations, which is a common experiment that uses this, those are always the things you want to make sure that you do when you're doing your experiment. You always take an initial reading and a final reading. If you don't do that, you just kind of waste your time because you won't be able to calculate the volume that you need for your calculation. So really something really important to remember, and also, again, give a proper reading. Any questions on that there? All right, so why don't you give this one a go, another burette, and what should the proper reading on this one? They're scaling 20 and 30. If we just subtract that, our large marking going to be 10 milliliters. In this case, if we count, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings between them. So again, if we divide that by 10, tells us our small markings here going to be 1 milliliter in this case. We're about at the second marking here. Remember, it does increase as you go down. So, oops, go back here. So we're right there at the second marking, which means it's at least 22 at that point. Again, 23 would be the next marking down. So we're at least at 22. So that clearly gets rid of this and this guy. So 22 for sure we should record. We know that if we take our smallest marking here, divided by 2, that's going to give us plus or minus 0.5 milliliters. So that tells us that we should be taking one of these, as that is incorrect, and that has too many digits. So in this case, we should go to only 1 decimal place, so 22.0 milliliters, as we feel it might be right on the mark there, plus or minus 0.5 milliliters. So that looks like this one here. This has the correct sort of uncertainty. Problem with this number is, how many significant figures is it? Yeah, it's only 2 significant figures. The uncertain number here is the second 2 in this case. So basically, if you took this guy, you're saying, I think it's 22, might be 23, might be 21. And again, that's a pretty big range of uncertainty that you don't want to put into this measurement, because you could do better. By the way, even though I sort of crossed this out earlier, the reason we wouldn't want to do this guy with 22.00 milliliters, how many significant figures would this one have? It would have 4 significant figures, as we record all the certain numbers and the first uncertain number. And the uncertainty would actually be here, which means in this case, what we're saying is, I think it's 22, but maybe it's like 21.99, maybe it's 22.01. We actually do not have the ability on this scale to go out that far. So as I mentioned earlier, putting extra numbers in, sometimes people think, well, let's put some extra numbers in to be safe, is not always correct, because you're now saying, again, in this case, your measurement is way better than it should be. And taking out numbers like the 22 by itself means that your measurement is actually worse than it should be. So again, that is the reason why we want to give our measurements to the proper number of digits, so we don't either overinflate how good our measurement is or make our measurement worse than it should be. Any questions on that there? So again, in this case, D would be the correct answer. All right. Any questions on taking measurements, how to take them? Again, when you take measurements in this class and pretty much all your chemistry classes here, they expect you obviously to take the proper number of significant figures. And also, like I said, in lab for sure, they usually want you to include the plus or minus, 0.5, 0.05, that type of stuff as well. Any questions on that there? So we've been talking really where significant figures come from. They do come from really measured numbers when you take a measurement. Let's talk about the official rules here again to figure out whether or not something is a significant figure. The first rule is pretty much all non-zero numbers, they are going to be significant. So we always start counting, by the way, left to right, and we start counting our significant figures when we hit the first non-zero. So in this case, we would start counting at the 1, and everything else behind it is a non-zero number. So they're all going to be significant. So that would be 4 significant figures in this case. Now, zeros can be a little bit difficult. There's 3 types of zeros. The first one's a leading zero, and these are not going to be significant. These are all the zeros that basically come before you hit the first non-zero number. So once again, starting left to right, we would not count that one. We would not count. We would not count. We're not going to start actually counting our significant figures until we hit the very first non-zero, which is the 4. And then the 9 is significant as well. So that would be 2 significant figures in this case, the 4 and the 9 at the end. There's also zeros that are trapped zeros or captive zeros. Those also are going to be significant. And again, we start counting left to right. So in this case, we would start counting at the 5. And now we have a couple of zeros that are trapped. So they would be significant. And that 4 is a non-zero number. It would be significant as well. So that's going to give us 4 significant figures in this particular case. Everybody is significant here. Probably the last one that gives people the hardest time is the trailing zeros. And these are zeros that come at the end of a number. And they are significant if there's a decimal point written in the number. Now, when you're counting significant figures or trying to figure out are these zeros at the end significant or not significant, the decimal point has to be there. So what I mean by that is, for example, when we did something like scientific notation that we talked about last time, even though there's not a decimal point written, we oftentimes will assume it's at the end of the number. And then we go and kind of move our decimal point where we need to. When you're counting significant figures, if their decimal point is not written, it does not exist in terms of significant figures. So it has to be written for you to sort of count it. So if we have something like this, which is 600, this would have how many significant figures? It would have 1 significant figure. It would be the 6 in the front. The 2 zeros at the end would be not significant because there is not a decimal point written in the number. So again, here, we don't assume it's at the end or anything like that in terms of significant figures. Now, if I wrote 600 like this with a decimal, how many significant figures would I have? I would now have 3 significant figures. Significant, these zeros at the end are significant because there is a decimal point written, and this would be 3 significant figures in this case. Questions on that there? Now, if I have 0.00040032000, call it centimeters, however I did that, I'm not sure. How many significant figures would this one have? What do you think? 1, 2, 3, 4, 34, 9? I honestly don't know because I was just writing numbers. So let's see. All right, so we'll go left to right. We're not going to count any of these. Right here at the 4 is really where we're going to start counting in this case, right? These zeros are trapped, so they are significant. So significant, 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 as they are non-zeros. That now brings us to the 4-pack of zeros at the end. Are they significant? Answer is no. The answer is actually yes, because way over here, there is a decimal point in that number. So the decimal point does not actually have to be right next to those zeros to make them significant. They just need to be written, the decimal point somewhere in the number, and then we'll make all the zeros at the end significant. So I think you're right there. So all these would be significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. Correct. Questions on that? Now, we talked about writing numbers in scientific notation. And remember that when we write a number in scientific notation, all the numbers that come before the times 10 part are significant. So if I write this number like this, 1.20 times 10 to the 4, this would have 3 significant figures, as all those numbers before would be significant. If I wrote 1.2 times 10 to the 4, and now we'll have 2 significant figures. So if it is written in scientific notation, all the numbers that come before the times 10 part are always going to be significant. And it's always before you like change it back into like decimal form. It's exactly how it's written in scientific notation in terms of the significant figures. We typically use significant figures for measured numbers. There are some numbers which are known as exact numbers, as we'll see on the next page. But exact numbers are basically one of two things. They're either definitions or they are something that is counted. So definition like 12 inches equals 1 foot. Counted like if I had 4 pens on my desk. I'm not going to do any type of scientific experiment to figure out how many pens I have. I'm just going to simply count, just count how many pens I have on my desk. So those are two things that are exact numbers. To deal with exact numbers, as we'll see here on the next slide, exact numbers can have really as many significant figures as you want because of that. And the good news is when we use those in calculations, we don't have to worry about exact numbers. We only have to really worry about measured numbers and significant figures in terms of our answer and where our answer should really end up. So it's really sort of important, that sort of distinction. As I mentioned before, in this case, for example, 12,000, how many significant figures does it have? You only be wrong once unless you get 2 answers. It is 2, yeah. So it does have 2 significant figures. Here, that is significant, that is significant. These zeros are not significant as there's no decimal point written in this number. The estimated digit in this case is which number then? The estimated digit is 2, yeah, not the 0, right? And it is the 2 here because that is the last significant figure. So this is what I was talking about earlier, that the estimated digit, the uncertain digit, is not necessarily always the last number that's written, but it is the last significant figure that is written in the particular number. Any questions on that there? So as I mentioned a second ago, exact numbers are either definitions like we see here, or something that is counted. And in terms of exact numbers, let's just box that up. As you know, they want you to know everything. So I would know these guys, yeah? So these are ones that will pop up. And you should know these. Once again, 1 inch is 2.54 centimeters exactly. 1 pound is, they want you to use 453.6 grams. 1 foot is 12 inches. A yard is 3 feet, and 1.609 kilometers in a mile. 9 pencils is an exact number, but that's something you don't need to know. It's just an example of something that's counted. So again, if you had like the classic textbook example is, you have like a basket of apples. If you're going to figure out how many you had, you would just count them and not do any type of measurement or something like that. So like I said, we will definitely come across exact numbers and calculations. And because they can have unlimited number of significant figures, the good news is we pretty much just kind of ignore them in calculations in terms of helping us decide how far we should take our answer to. Questions on that? All right, so again, going left to right, not going to count until we hit our first non-zero, which would be the 3. Now we're going to count. We got a trap 0, which is significant, and we got a non-zero. So significant, significant, significant. We should have 3 significant figures in this particular case. Question on that one there. Here we got scientific notation, which again is written in scientific notation for a reason. Basically, everybody there before the timestamp is going to be significant, and that's going to give us 4 significant figures. Again, as I mentioned, sometimes people fall into a wrong trap when they're trying to figure out significant figures with scientific notation is they will kind of turn it into decimal form and then get the wrong number of significant figures. So however it's written in scientific notation is how many significant figures you should have. And technically speaking, if you turned it into decimal form, it should still have the same number of significant figures as well. We got 125, so starting here, everybody's a non-zero, so 3 significant figures. Our 10 written like this, that is going to be 1 significant figure. Our uncertain number in this case is actually the 1, right? That's a 0 is not significant as there is no decimal point written. And lastly here, going across, we got starting to count here. That is trapped, so that's significant, significant, significant. This 0 at the end is going to be significant because there is a decimal point there. So now we have 4 significant figures. Question on that. As we also talked about last time as well in terms of scientific notation, remember that in certain cases, there may be only one way to get the proper number of significant figures is to write in scientific notation. So if we go back, for example, to our 12,000 we talked about a second ago, that has obviously 2 significant figures. But let's say we wanted an answer with 3 significant figures, right? So let's just say we did a calculation, and on our calculator, this is what it spits out to us. But we really need to give the answer to 3 significant figures. We can do this, right? But how many significant figures would it have in this case? It would have 5 significant figures in this case, right? Which is no good. I could do 120. That has how many significant figures? 3 significant figures. Is that good? That is not good because there's a very big difference, right, between 12,000 and 120, right? So if I owed you $12,000 and said, "Hey, I'm going to round you 3 sig figs. Here's 120 bucks," you're not going to be very happy with me, I imagine, right? So there's a very big difference in that meaning. So although it is to write sig figs, the meaning is different. There really is no way to do this other than writing something in scientific notation. For example, 1, 2, 3, 4. And now we have something that has 3 significant figures and it maintains really the meaning of the number. So it's really important not to go crazy with the rounding per se and not change the meaning of the number. But there will be certain times where the only way to give the right answer is you have to do scientific notation because you can control how much significant figures you want. Like I said before, if I wanted only 2, I could just write 1.2 times 10 instead of 4 and so forth. Any questions on that there? So speaking of rounding, we really don't want to do any of those extreme roundings like I just talked about. But the rounding rules are pretty basic. If the digit that you're going to stop at, if the next digit is 4 or less, we typically just drop the numbers. If the next digit where you're going to stop is 5 or more, we do round up. Now, again, if you had 0.44567 and we wanted 3 significant figures in this case, we would go 1, 2, 3 would be here. We would look at the next number. So that's where we want to end. We would look at the next number and we see that it is above 5. So we would round this to 0.446 in this case. if I had 0.045224 and I wanted 3 significant figures, we would go 1, 2, 3 significant figures would be here. We would take a look at this guy and go 0.0452 and maintain our 3 significant figures in this case, right? So if I have 13,333 and I want 2 significant figures, what should the answer be for 2 significant figures in this case? Would it be 13? Yeah. Or would it be 13,000? Yes, sir, in the back.
Yeah. I forgot my answer. My fault.
No worries. Which one should it be? How many significant figures does each of these have? We'll start with the guy on the left. How many significant figures does this have? That's not the trick question. Tell me. 2. There you go. That's 2 significant figures, right? This guy has how many significant figures? Does have 2 significant figures, right? So they both have 2 significant figures. So we come back to the idea of, do we want to change this number? So again, a good way to always remember it is somebody owes you $13,333 and they say, here's 2 significant figures, here's $13. That is probably not going to fly, right? Again, there's a very big difference between 13 and the number 13,333. This is not too bad. It is 2 significant figures. It still maintains the value there. So maybe I get like a $333 teacher discount, right? It's all right. It's still about 13,000 bucks. So that's not too bad. And it doesn't change the meaning of it. It happens a lot with people always trying to get the right number of significant figures, which you should do. But sometimes when people try to get the right number of significant figures, they go like extreme rounding to get the sig figs and change the meaning of the number. So you never want to do that. Obviously, other ways that you could give the answers in these cases is you could also lay up 1.3 times 10 to the 1, 2, 3, 4, little scientific notation, and that would be 2 significant figures written like that. Would I want to write 1.30 times 10 to the 4? How many significant figures would that have? I have 3, too many, right? Also, why I would not want to write 1.3000 times 10 to the 4, because then it would have 5 significant figures. So again, you got to watch that out. You could also obviously do scientific notation on any of these as well, 4.52 times 10 to the minus 2 in this case. So you could have done, scientific notation on that as well. So for me personally, you don't necessarily have to give the answer in scientific notation unless the instructions say to do so. But again, sometimes the only way to get it to the right sig figs is to do scientific notation. Any questions on that there? Okay, so looking at this here, we want to go each of these to 2 significant figures. So looking at the first one, our second significant figure is right there at the 5. That means we do need to look over here at the next one, which is a 7. So that is going to round up. So that's going to give us a 36 meters in this case. Questions on that one? Take a look at the next one. We are at the 8 as our second significant figure. Here we would look at the 2. That is less than 5. So we basically will get rid of it. We can't get rid of it in this case because we still need the zeros to maintain the meaning of the numbers. So the problem again here, if I write 38 grams, although it does have 2 significant figures, that is nowhere near the meaning of this number. So although it is the right number of significant figures, it is incorrect in terms of what it means. I could also not put a decimal point at the end of that number, right? Because then I would have 4 significant figures. So you can't do that either. This is also one, obviously, you could scientific notation if you wanted to. 3.8 times 10 to the 1, 2, 3. Here we would not include the zeros because, again, it would give it too many significant figures in scientific notation. So we have to keep it at 3.8. Question on that there. Yeah. Is in terms of these 2 here? No, it's not. So again, like I said, as long as the instructions don't say give your answer in scientific notation, either one is perfectly fine, whichever way you prefer. If it does say scientific notation, then obviously you need to get the one on the right there. They're both correct. So really for us, what you should be shooting for is correct number of significant figures, and however you want to achieve that, it should be okay. I would highly recommend, though, like we talked about with scientific notation, to use it if you have a lot of numbers and stuff like that, rather than run a bunch of zeros, obviously, and stuff like that. Other questions? All right, so here, second significant figure is at the 6. We're going to look at the 2, which is where we're going to help us decide. And the 2 is less than 5, so we are going to drop it in this case. Why did I not leave them as zeros at the back end here? So why did I not write the answer like this? Yeah. Exactly right. Because in this particular case, we have a decimal point. That would make these zeros, if we put them, significant, and that would give us 4 significant figures, which is not what we're looking for in this case. So in this case, we do need to completely drop them. And it doesn't change the meaning of the number here. It's basically the same meaning. So we're good to go. This also, you could scientific notation 2.6 times 10 to the minus 3 in this case as well. So you could have done that if you'd like. Lastly here, our second significant figure there, we got an 8. We're going to round up 1.3 kilograms in this case. Any questions on that? Now, let's talk a little bit about rounding and doing calculations. You definitely should, in most cases, not round until you get to the very end of your answer. You should definitely keep track of everything, like how far you should take, each of the measurements or calculations. But if you're going to do a calculation, for example, you did a calculation, you got a number, then you're going to take that, do another calculation, get an answer, take that, do another calculation, get an answer, and so forth, like a bunch of sort of calculations in a row. It's really good practice not to round to the very end, because if you round a little bit after the first answer, then round a little bit after your second one, and then the third one, you will find yourself with an answer that's pretty far away from the right answer and stuff like that, because you kind of rounded away a lot of it along the way. You'll have what's sometimes referred to as rounding error. What should you do? Honestly, a lot of people keep some extra digits. So if you need to write a number, maybe, you keep a few extra digits. And then maybe you just kind of mark where you should technically stop, right? So that little line sometimes people will use to indicate, okay, that's kind of where, if I were to stop the calculation, that's where I should end with like significant figures, but I'm going to keep a couple of extra just in case. And usually that will kind of help you avoid those kind of rounding mistakes and stuff like that. Personally, for me, I just roll with whatever's in the calculator. Yeah, so I just roll with the whole number in the calculator. I clean it up at the very end, and usually you won't get into any type of rounding error situation in that along the way. But if you want to keep some guard digits, if you need to write a number down or something like that, don't strongly round until the very end, unless that is the last part of your calculation. Then at that point, obviously, you could round. Any questions on that there? So speaking of calculations, let's talk about how we determine significant figures in calculations. So there's basically kind of 2 sets of calculations that we do. We multiply or divide, or multiply and divide. And if you multiply or divide, what you are looking for in terms of your answer, how many significant figures your answer should have, is based on whatever number has the least number of significant figures. So if you're multiplying or dividing, so if you took 423 and you multiplied it by 0.22, see, as we're multiplying here, we would look at significant figures. This number here has 3 significant figures. This number here has 2 significant figures. That means when I get my answer should have 2 significant figures based on the smallest number of significant figures. Same thing if you're dividing. If you had like 2.35 divided by 123, this number here is 4 significant figures. This number here is 3 significant figures. That means when we get my answer, 3 significant figures is what we should have. So for example, here, if we took our first one there, 423, we times it by 0.22. On our calculator screen, it is going to give me 93.06. Once again, it doesn't give you the right sig figs, your calculator usually in most cases. Here, we would want to go to two significant figures, which is here. We would look at the 0, and this would be 93, would be our proper answer here. If we divided our top one there, which is 32.35 divided by 123, on our calculator screen, it's going to give us 0.26300,813. Here we would look at three significant figures, which would take us to here. So the proper answer would be 0.263 in this particular case. So if you're multiplying or you're dividing in a calculation and you want to know, how far should I take that answer to, it is the number of significant figures you're looking at, and it is the least number of significant figures is what your answer should have. Any questions on that there? Now, when we add or subtract, we're actually looking at something different. We're looking at decimal places rather than significant figures. It is the same sort of idea. It is the least number of decimal places. The idea behind this is significant figures deals with measurements, which means your calculation is only as good as your worst measurement. So your least number of significant figures, your least number of decimal places, that's, for the lack of a better description, your crappiest measurement, right? And your measurement or calculation is only as good as your worst measurement. And, like that old saying, you're only as strong as your weakest link. So whichever one is sort of the worst is as good as you could kind of give your answer to. So when we add and subtract, we're looking at decimal places, not significant figures. So if we had 42.225, we added 1.3 to it, and we added like 2.43 to it. And we add all that together on our calculator, 42.225 plus a 1.3 plus a 2.43. So on your calculator there is going to show you 45.955. Here we're looking at decimal places. So this has 3 decimal places. This has 1 decimal place. This has 2 decimal places. Smallest is 1. We would go here. So interesting choice of numbers there. We would look at the next number here, by the way, and we would need to do some rounding, right? Which means I actually would then need to, in this example, round a little bit more that way, right? And I should end up with 46.0 in this case, yeah, based on the rounding that we should end up with. I should still have the 1 decimal place. So even though this rounds up to 46, I should not write 46 because that's incorrect, right? We could go to 1 decimal place. So even on the weird rounding that we just got there, we want to make sure we still maintain it. Although it does have 1 decimal place, how many significant figures does it have? It has 3 significant figures, right? And that could be important if you're going to go and take that number and do something else with it, multiply it, divide it, and so forth. So when we add or subtract, you're looking at decimal places. When you multiply or divide, you are looking at significant figures. In each case, it is the least amount of either of those decimal places or significant figures. Questions on that? Again, this is typically for measured numbers. If you have an exact number, you really don't have to worry about it in its calculation at all. So if you have an exact number and you can identify as an exact number, you don't have to worry about it in the calculation. Now, if you did a multiple of stuff, so let's just say we have 32.3, and we times it by 0.4444, and we divided it by 1255 there. So in this case, we're doing a lot of things here. The first thing that you probably would do is what's in parentheses, right? So if we multiplied the top part there, 32.3 times 0.444, one more 4. There we go. On our calculator screen for the top part, we got like 14.35412. Now, if we were looking at the top part, we are multiplying, so we're looking at significant figures. This technically has 3 significant figures. This has 4 significant figures. That means, technically speaking, when we get our answer for the top part of it, it should actually have 3 significant figures, right? Which means technically we're right about there, right? Would I round at this point to 14.4? The answer is no, because I'm going to take that number now, right? And I'm going to divide it by the bottom number. But I will keep track of perhaps where I need to be. So I'm now going to take that number essentially and divide it by this number, which is 12555, which has 5 significant figures. And this guy technically should have 3 significant figures. But so I do not get any rounding error, I'm going to take really the whole number is still in my calculator, and I'm going to divide by 12555. And that's going to give me on my calculator screen here 0.001143299. Now I know the very last thing that I did was divide, which means I should be looking at significant figures. Smallest number of significant figures is actually 3. My final answer should end up right there. We would look at this guy, and in this case, we would drop the rest of it, and we would end up with 3 significant figures. So it's really important not to round too much, and also keep some guard digits if you are going to do a little bit of rounding, so you got a couple extras, and then clean it up at the end, but you can't keep track of it. This goes for everything from what we just did there. For example, if you were going to say, I don't know, we'll do, let's say we have like 52.55 grams, and we're going to divide it by like 24.5 minus, and we'll do 23 milliliters in this case, right? So again, in this case, if we were probably going to do this, right, we would actually do the subtraction first, right, because it's in parentheses. So we would have 52.55 grams. We'd do our little subtraction there, 24.5 minus 23 gives us 1.5 milliliters. That 1.5 milliliters should go to 1 decimal place, as these guys were 1 decimal place, right? And we're subtracting. The final thing we're doing now is going to divide those two numbers. So we'll take 52.55 divided by 1.5. That will give us, on our calculator here, 35.0333, a bunch of threes going, right? A whole bunch of threes. Now, the last thing we did is divide. This has 4 significant figures. This has 2 significant figures, right? Remember, it has 1 decimal place, but now we're dividing, so we're interested in how many significant figures it has. That means my answer actually should end up with 2 significant figures, and it should be 35. By the way, grams per milliliter, the units don't cancel, they still stay, and you end up with something in that nature there. Question on that. All right, so we will lay it up there. I think